So in the last video, we talked about fundamental theorem, and fundamental theorem had a lot to say, right? The fundamental theorem, and we had an example, the integral of from 0 to sine x of t squared dt equals sine squared x times the cosine of x. And remember I said, well, if we let u equal sine x, right? So we would have the integral from u to 0, so the derivative. There you go. The derivative from t squared dt, that would be what? It would be, well, what's the integral though? Well, the integral would be what? T to the third over 3 from 0 to u times the derivative with respect to x. This is going to be u to the third over 3 minus 0. And if we take a derivative, well, what was this? What was u? Well, let's take a derivative. Can we take a derivative of this? Well, this is d... Well, what is this? Well, the derivative of u to the third over 3 is u to the second. Well, but this is chain rule, or implicit. But it's chain rule. So d times the inside, which is du dx. What's du dx? Well, it's cosine x, right? So it's sine squared x times the derivative of u with respect to x. That's where we came from. So if you have, and the general case, I'm sorry if you didn't have to write that down, is you have to write this one down. If we have the derivative of a constant to some function of x, so if we're integrating from a to some function of x, of some function of t dt, this is going to equal f of g of x times g prime of x. Have you seen this before? You have. But that's what that is. That's the general case here. Okay, so I gotta hurry up. I can't cover this any longer. Put that in your notes. You'll be good. So we're done talking about the fundamental theorem. And we're kind of done with Calc 1, not really. There's a bunch of sections left. They're all for applications. We're going to have to cover this. The applications go to the technical way of doing what the derivative does, what the integral does, what it all does. Really, for us, it doesn't go for integration rules, differentiation rules, it doesn't go for those kind of things. But we're going for applications. And the first one is going to be increasing slash decreasing. So increasing slash decreasing, and the first derivative test. I'll put dy dx, but the first derivative test. Okay. So you know functions, right? If I have a function next, and I just drew it like that, and now let's say, let's call this A, right? I'll call it C, or not. So, and these go on forever, but we'll just cut the points from here and whatever. So this is A and this is B. So let's talk about increasing and decreasing of our function. Is our function what's happening from I won't put brackets, I'll put open, from A to C? What is our function doing? Is it increasing or decreasing? It's increasing, right? So this is increasing. What's happening from C to B? It's decreasing. So if this is f of x, what do you notice? What do you notice about f prime of x at A and C, from A to C? So from A to C, f prime of x, I'll draw a tangent line. What is the slope here? It's positive or negative? It's positive. What about here? It's positive. What about here? It's positive. Here, positive. Here, positive. So, notice the pattern. When my function's increasing, the derivative is greater than 0. It's positive. So, that means it's increasing. So if f prime of x is greater than 0, f of x is increasing. Yeah, we're up from C to B. What happens to f prime of x from C to B? Well, what's the slope of here? Is it positive or negative? It's negative, right? Slope here is still negative. This is still negative. This is negative. That's still negative. The slope is negative when the function is decreasing. So if the function or the derivative is less than 0, then your function is decreasing. But what happens at C? Well, at C, the derivative is 0. Oh, so this is kind of an important one. If f of x, if f prime of x equals 0, then f of x has a critical point. Critical point. If our function has a critical point, there is something called relative extrema that can happen at that point. This extrema is what you call a minimum or a maximum of a graph. So notice if I draw this curve, you will notice that all relative extrema happen when f prime of x equals 0. Right? But f prime of x equals 0 says that f of x has a critical point. And we can draw the conclusion that, well, relative extrema occur at critical numbers? Question mark? The answer is not always. If we have relative extrema, then the point at which there is an extrema, that point is a critical number. But if we get a critical number, it doesn't mean we have a relative extrema. And that is why we call it the first derivative test. Is we're testing our critical points for f prime, for f of x. But we're putting it into f prime of x to see, is it going to be one of these two? So I'm going to show you how you do it with one example, and we'll be good. So if I had f of x equals x squared plus x, I want to perform this first derivative test and find out all my relative extrema. I kind of also want to point out all the points that is increasing, all the where it's increasing or decreasing. I want to find where the function is increasing and decreasing, and I want to find where f of x has a maximum or a minimum. Now, before we go on to the test, I want to tell you two cases. Maximums and minimums. So here's a maximum, here's a minimum. So, if we look at this, that's obviously the point C for critical number, or for critical point. These are the points C. Now on either side is an interval, and I'm going to test f prime of x on the interval. So what is f prime of x from, or before C, for numbers less than C? Well, for numbers less than C, f prime of x is positive. Well, numbers after C in this case are going to be where f prime of x is negative. So notice, this is a maximum, right? So therefore, how would you know if this is a max? Well, if the function changes from increasing to decreasing, you're going to have a maximum. If we go for minimums, what is f prime for numbers less than c? It's negative. Whereas for numbers greater than c, it's positive. So if we have a function who changes from decreasing to increasing, from decreasing to increasing, that critical point is a minimum value. No, not minimum, sorry, minimum. That's the way you distinguish from minimums and maximums. So you'll know if it's a relative extrema, if it changes from increasing to decreasing, or from decreasing to increasing. If the sign does not change, therefore the critical point doesn't give us relative extrema. Okay, let's do x squared plus x. How do we find critical numbers? Remember when I had that on the board? When f prime of x equals 0, right? Well, this is f of x. We want to find f prime of x. So what is f prime of x? Well, it's 2x plus 1. Okay. Well, what did it say? It said f prime of x equals 0. That's when critical points occur. Well, let's set f prime of x equal to 0. Let's solve it. So x is negative 1/2. That's our only critical point or number. So let's test that. So I'm going to make a little test that says, well, I'm testing negative 1/2. And I'm using the first derivative test. So if I plug in a number less than negative 1/2, like negative 1, into my derivative, not my function, in the derivative, I'm putting values for f prime of x. So if I put negative 1 into f prime of x, am I going to get a negative or a positive number? Well, in this case, I get a negative number. Okay, how about, let's pick a number that's bigger than negative 1/2. Let's pick 0. Well, it's going to be positive. What does this tell you? This tells you that f of x is increasing on this interval, and it is decreasing on this interval, and it has a relative, well, it's going from decreasing to increasing, so it's a relative min at x equals negative 1/2. Now you can plug that into the function, and you can get back the value of your minimum. So that is the first derivative test. I'm not going to show you more examples that are harder, because I think you got the process, right? Ooh. There's another case. Critical numbers occur when f prime of x equals 0, and when f prime of x is undefined. So, and sometimes, when we take a derivative, and we have sometimes when it's undefined, that means there could be a relative maximum. At where the derivative is undefined? What are you talking about? Well, what could possibly the graph look like if we have a relative extrema when f prime of x is undefined? Where would that possibly be? Right here. This is called a sharp point. And this function isn't differentiable everywhere. It is differentiable everywhere except this point right here, because it's a sharp point. This is where the derivative is undefined. But it's a relative maximum, right? So therefore, we can prove that, well, points where f prime of x is undefined are critical numbers because relative extrema can occur at them. Okay. Let's talk about some theorems that are important. There's something called Rolle's theorem. Rolle's theorem. And there's something called the mean value theorem. Let's cover mean value theorem first. So Rolle's theorem and mean value theorem. Mean value theorem says, hey, let's say we have some function. In fact, I'm going to do this. I'm going to go from there. If I have A and B and f of A and f of B. Okay. What is the rate or what is the secant line through A and B? Let's see this. What would be the slope of the secant line? Well, the slope of the secant line equal, like it looks like that, right? Wait, can we draw a tangent line that has the same slope as the secant line? Yeah, right here. Wait, this is some value C. Some value C where the derivative of this function equals the average rate of change from A to B. Ooh. So this is what this is what the mean value theorem says. Well, if you have a continuous differentiable function, then from A to B, closed circle, the average rate from A to B is this. And there's some value C that's in the interval where f prime of C equals to the average rate of change. That's mean value theorem. Rolle's theorem. Rolle's theorem says a little bit something different. Rolle's theorem. Look at this Rolle's theorem. This is what Rolle's theorem is saying. Rolle's theorem 172. So Rolle's theorem is pretty easy. It's saying, hey, my function has 2 points, A and B, where f of A equals f of B. It has to be true. f of a equals f of b. And if the function is continuous, draw a function that is continuous, it will guarantee some value c on the interval where c is a relative extrema. It guarantees the existence of such value c on A to B where c is a relative extrema. That's what Rolle's theorem is saying. Ooh, but what is that saying? Well, that's also saying that f prime of c equals 0. That's what it's saying. That f prime of c equals 0. So Rolle's theorem is saying if your function is differentiable and continuous on the interval from A to B, then there's some c inside of A to B. Ooh, but f of A equals f of B, where f prime of c equals 0. Which also has to mean this relative extrema, right? There you go. Mean value Rolle's theorem. And I think that's it. There's some examples on these, like find value c. Well, for this one, you have to just take the derivative and plug in c. Find average range. Find where c equals that number. That one's pretty easy. So we're going to use Rolle's mean value theorem kind of for intuition. And that's it about Rolle's mean value theorem.